Hello students, welcome to Narayan PU College online classes. So in the last video we have discussed about the 17th group elements. So in the B block we have completed 15th, 16th and 17th group elements, and the next one and last one is 18th group elements. Clear? So as we have discussed in the previous, and total 10 marks will come from this chapter and three marks question and one mark question. Most of the time 1 mark question is asking from 18th group elements. Clear? So we will discuss what are these 18th group elements, properties, physical properties, chemical properties, all we will discuss one by one. Clear? So first of all we will write what are the elements present in the 18th group elements. Clear? So the first one here, write element and symbol. Element and what is my symbol. Clear? So you make one table here. So the first one is helium. So what is the first element here? Helium. The first element is helium. The symbol is He. Next one is helium neon. Neon symbol is Ne. Argon. Helium neon argon. Argon is what is here? Ar. And the next one is krypton. Krypton is Kr. Xenon. Xenon is Xe. Clear? Radon. So radon symbol is here I. So these are about the elements which are present in the 18th group. Yeah. So here helium He, neon Ne, argon Ar, krypton Kr, xenon Xe, and here radon Rn. These are about the elements present in the 18th group elements, and these elements will be called as which one elements here? 18th group elements. 18th group elements. 18th group elements. Or if you don't consider the D block elements, and can also be called this one as a 8th group elements. 8th group elements. Clear? So you know that these all are gases only. These all are which one here? Gases. So 18th group elements all are gases. They are, except radon, they all are present in small quantities in the atmosphere. Clear? Except radon, remaining all gases, all noble gases, or we can say 18th group elements are gases present in the atmosphere in small quantities. So that's why these gases can also be called as a rare gases. Rare gases. Clear? And also known as aerosols. Clear? So why? Because they are present in air, so that's why can also be called as a aerosols. Clear? And now these elements, and these elements, helium, neon, argon, krypton and radon, and these 18th group elements do not show chemical reactivity at the room temperature. They will not react with any others or itself at the room temperature, and so that's why these are also called as inert gases. Inert gases. These all are gases only. That's why we are calling these are inert gases. Clear? But later, and compounds of xenon and krypton have been prepared. Clear? So what that it suggests? It suggests that these gases are not completely inert. Clear? They are not completely inert. So that's why, and they are, this name is changed to noble gases. Clear? So what it is here? Noble gases. Why this name has been changed to noble gases? Because and it is analogy with the noble metals. Noble metals we have already know what it is. Gold and platinum, they are very reluctant to react. Rather than complete inertness, they will react, but they are not completely inert. So here also they are inert but not completely inert. So that's why, and from that they have mentioned the name here noble gases. So these are the names of 18th group. Clear? So what it is here? So elements you see, we have elements helium, neon, argon, krypton, xenon, and radon. And helium, neon, helium symbol is He, Near, Kr, Xe, and Rn. These are the symbols of 8th group elements. So these all elements are belongs to which group? 18th group. And if you don't consider the D block elements, can also be called as 8th group elements. Clear? And these all are gases except radon. Except what is radon. Remaining all gases are present in small quantities in atmosphere. So that's why these called as a rare gases. They are present in the air, so that can also be called as a aerosols. They do not show any chemical reactivity at room temperature, so that's why they called as a inert gases also. Clear? But and some of the compounds of xenon and krypton have been prepared later, so that's why, and this name has been changed to noble gases. Noble gases means what it is here? They will show the means they are very reluctant to react, but rather than the what is complete inertness. They are not completely inertness. At some time, and with some compound, highly electronegative compounds or highly electronegative elements are at very high drastic conditions, with some elements they may react. So that's why they mentioned here what is here noble gases. Clear? So next one here is electronic occurrence is there. Put the heading. Next one is occurrence. This is brief discussion about the what is here 18th group elements. So next one, put the heading occurrence. Clear? Put the heading here is occurrence. Just now I mentioned, except radon, remaining all noble gases are occurs in the atmosphere. Clear? They are present in where? Atmosphere. So their abundance in dry air is about 1% of 1% by volume. How much percent they are present in the air? So totally it means all noble gases, and they are present 1%. They are present in the volume in the air by volume. Clear? Of which argon is most abundant. Clear? So they are present about 1% by volume in the air, but among all the noble gases, and argon is the most abundant in the dry air. Clear? So one more question. Sometimes one time they have asked in the PU examination. So which of the following noble gas is most abundant in the air? Clear? So what is that one? Here, argon. Clear? And also here neon is there and helium. Mainly what it is here? Helium. And sometimes neon. Helium and sometimes neon. They are found in minerals of radioactive origin. Radioactive what it is origin. So helium and sometimes neon, but most of the time what is helium, and are found in minerals of radioactive origin. Clear? So what are those minerals which radioactive minerals means? Clear here? And pitch blende. This is, and another one is monazite, clavite. So these are the radioactive element. Mainly helium is found in this radioactive minerals. Clear? And very important here is next one. And the main source for the helium is natural gas. This is also one time they asked for one more question in the PU examination. Clear? So what is the main source for the helium? What is the main source here? Natural gas. Write that one also. Here, the main commercial source, the main source for helium is what it is, my dear? Natural gas. Natural gas. The natural gas is the main source for which one, my dear? Helium. And the next one is, and xenon and radon. These are rarest elements of this group. Clear? So which one here? Xenon and what it is? Radon are rarest elements. Rarest elements of the group. Rarest elements of the which one here? Group. But here radon is obtained by the decay product of radium. Clear? So radium, when it undergo decay, when it undergo decay, it releases alpha, beta, gamma, rays. So and when it undergoes, radium undergoes disintegration, and what it will form here? Radon. So that is here radon. Radon is obtained. Radon is obtained by decay product of what it is here? Radium. Decay product of what it is here? Radium. So radium, if you say the atomic number of radium is 88 and here 226 is the mass number. And if it undergoes decay, means it releases the alpha particles. Clear? When it releases alpha particle, what we have to write here? Alpha particle means what? Helium. Helium 2 and 4. Now 82 and 2 already is left here, so you will get here radon and 86 and 222. Clear? So 222 plus 4, 226. 86 plus 2, 88. So here what we are getting here? We are getting radon. By which one? Decay of radium and gives the radon. So this is also one time they asked in the examination. So these are about what it is here occurrence. So where they are occur and the noble gases are, except radon, noble gases occur in atmosphere. Clear? So in that one, these are the abundance of these noble gases in the dry air is about 1% by volume. And among them, so argon is the most abundant. Clear? And helium and sometimes neon, they are found in a minerals of radioactive origins. Those are pitch black, monazite, and chloride. And the main source of the helium is natural gas. And radon and xenon are rarest element. And radon is obtained by the decay product of which one here? So next one is electronic configuration. Put the heading electronic configuration. Electronic configuration. So if you take here electronic configuration, so we will draw one table here. First one, what it is here? Element. Yes. After then symbol, atomic number, and electronic configuration. Atomic number and what is it? Electronic configuration. First one is here. You already know that helium. What is the symbol of helium? He. What is the atomic number of helium? 2. What is the electronic configuration? 1s2. Clear? And the next one, helium, neon. Clear? What is the neon symbol here? Ne. What is the atomic number here? Add 8. 2 plus 8. 10. So what is the electronic configuration? How to write electronic configuration? Shall I write here? Helium. So 2s2. 2p6. And here, very important, I forgot to say, the general electronic configuration for the 18th group elements are ns2, np6. Clear? What is the general electronic configuration for 18th group elements? ns2, np6. Clear? So here, helium 2s2, 2p6. Helium how much? 2 plus 2, 4 plus 6, 10. Clear? So next one, helium, neon, argon. Clear? So argon, what is the formula here? Ar. And compared to the remaining elements, means 17th group and 18th group, one element extra comes here, helium. One extra element comes here. So that's why 2 times you have to add 8 and 2 times you have to add 18. Previous 8, 18, 18, 32. But now 8, 8, 18, 18, 32. So that's why we add another 8 here. Means 10 plus 8. What do we get from here? 18. So 18 means what we can write electronic configuration? Neon. And 3s2. What it is here? 3p6. Neon how much? 10. 10 plus 2, 12. 12 plus 6, 18. Clear? Helium, neon, argon. Next one is krypton. Clear? Krypton. What is the krypton formula here? Kr. So here 18 you add 18 plus 18. 36 is the atomic number. Clear? So 18 plus 18, 36. Then how to write here? Argon. You know this is argon. And next what you will get? 4s2, 4p6. And before that, you know this is 18. 18 plus 2, 20, 20 plus 6, 26. But how much you have to get? 36. So that's why next electrons will come into the 3D. Clear? Krypton. And next one is xenon. Xenon, what is the formula here? Xe. So, and 18 you add, then what you will get? 54. Clear? So, you will get here krypton. Clear? So, here 5s2, 5p6 along with that, and 4010 also will come. Clear? Because it is the 36. Clear? And radon, last one is radon. It is a radioactive element, radon. So we will not much discuss about this radioactive. And 32 if you do, if you add 86. 86 means what you will get here? Xenon, 6s2, 6p6 and 5d10, 4f40. Clear? So this is about what it is here? Electronic configuration. And symbols we have written here, and atomic number and electronic configuration. So next one is here physical properties. Okay? So first we will discuss here in the physical properties atomic radii. What it is here? Atomic radii. So atomic radii. If you compare atomic radii of the 17th group and 18th group, so which one will have and large atomic means more atomic size here? You know large size will be 17th group. Why? Because when we are moving from the left to right, so what will happen? Atomic size decreases because nuclear charge increases. But as we are moving down from the helium to radon, down the group, automatically atomic size increases because you already know number of shells increases. So that's why atomic radii, if you see helium and they are less than helium, neon, argon, what it is now, krypton, and less than xenon, and less than radon. Radon is having the large size. Clear? So as we are moving down the group from the helium to argon, atomic size increases. Argon is a large molecule and helium is a small molecule. And this is about the atomic radii. And next one is ionization enthalpies. Ionization enthalpy. Clear? So next one is ionization enthalpy. Clear? So you know that here ionization enthalpy. What is meant by ionization enthalpy? The energy required to remove the outermost electron, that will be called as a ionization energy. Clear? But you know here and noble gases or 18th group elements have very high ionization enthalpy values. Clear? Why? Because of stable electronic configuration of the 18th group elements. You know what is the general electronic configuration of 18th group elements here? Ns2, Np6 means here how many electrons are there? And 2 electrons. In the p orbital how many electrons are there now? 6 electrons. Remember this is 6 electrons. So it is what is now? Fully filled orbital, fully filled orbital or off filled orbital. And that configuration is very stable. If it is a stable, to remove the electron from that configuration, you have to supply a lot of energy. Clear? So that's why and ionization enthalpy values for the 18th group elements are very large. Clear? So that's why and write that point here. And the noble gases have noble gases have a very high ionization enthalpy values. Ionization enthalpy values. Clear? Due to which one? This is due to stable electronic configuration. Stable electronic configuration. So due to the stable electronic configuration, and we cannot remove the electron easily, so we have to put a lot of energy. But you know, ionization enthalpy values, as we move down the group from the helium to radon, automatically atomic size increases. Atomic size increases means nuclear charge on the outermost electron decreases, so removal of electron is very easy. So that's why as we move down the group, then automatically ionization enthalpy values decreases. Clear? So that is ionization enthalpy values down the group, what it is not here, decreases. Means helium, neon, argon, krypton, xenon, and last one is what is not radon. So this is ionization enthalpy value of R. Helium will have highest ionization enthalpy values. Clear? So this is about ionization enthalpy. And the next one is here. Very important, third one, electron gain enthalpy. Electron gain enthalpy. Electron gain enthalpy. So noble gases have, electron gain enthalpy values of noble gases are positive. Till now you see previous we have discussed. And the electron gain enthalpy values means always they are in the negative values. Clear? Why negative? Because you know that. And they need electron, means 17th group if you take. 17th group is one electron less to get the noble gas electronic configuration. So that's why it has very high tendency to accept the electron to get the stability. Which group here? 17th group. If I compare my 17th group, what is the electronic configuration? General electronic configuration. Ns2 Np5. Ns2 Np5 means 1, 2, 3, 4, and here what is 5. One electron is less to get the stable electronic configuration, so they have very high tendency to accept the electron. When they accept the electron, they get more stable. When they get more stable, from less stable to more stable, when they are converted, energy will be released. That we will call as a electron gain enthalpy. When we add the electron, some energy will be released, and that we will call as electron gain enthalpy. So energy released means the values are in the negative. But if you take the 18th group elements here, what is the 18th group? What is the electronic configuration? This is the electronic configuration Ns2, Np6 here, Np6. Clear? So these 18th group elements have no tendency to accept the electron because already they are stable. Why they have the tendency to accept the electron? They don't have, or they do not have any tendency to accept the electron. So that's why if you wanted to add the electron will be added in next higher energy level electrons. Clear? If you want to put electron in the next higher level energy orbital, you have to supply a lot of energy. Why? Because it is a stable configuration. Clear? Stable configuration, if you add one electron, it becomes unstable, so it won't agree. So that's why they don't want to take the or accept the electron. So that's why if you want to add that electron, you have to put the lot of energy. You are giving energy, you are supplying energy. So that's why, and the electron gain enthalpy values for the noble gases are positive. Clear here? So that is clear. So very difficult to add the electron here because already stable, so it won't agree. These elements will not agree to add the electron. So that's why, and here electron gain enthalpy values, electron gain enthalpy values for noble gases are positive. Noble gases are which one here? Positive. Clear here? So you know, and as we are moving down the group, automatically the electron gain enthalpy values decreases. Clear? So this is about what it is here, electron gain enthalpy. Next one is monoatomic nature. Next one is what it is here, monoatomic nature. Clear? So you know, these all noble gases are monoatomic. Clear? Monoatomic means what? They are in the form of helium is the He. Clear? So these all are monoatomic and colorless, tasteless gases. Clear? So that is, and all noble gases are monoatomic and colorless, tasteless gases. Tasteless what is here? Gases. Clear? So why they are monoatomic? Because of their stable electronic configuration, even they do not combine themselves also. To combine themselves, at least they need one unpaired electron, so they don't have any unpaired electron. So that's why, and this is because this is due to monoatomic nature is due to its what it is ma, and monoatomic nature is due to their stable electronic configuration. Okay, no? So this is about which one ma here, monoatomic nature. And the next one is here, fifth one, melting and boiling points. Melting and what it is ma here, boiling points. The melting and boiling points of noble gases are very low. Clear? Why? Because means these atoms of these elements, they are held together by a very weak van der Waals forces, can also be called as dispersion forces. Clear? And in the liquid state or in the form of gaseous states also. So that's why, and you know, they have very low melting and boiling points. Clear? So write that point. So melting and boiling points of noble gases are very low. This is due to, this is what it is here, due to all the atoms of these elements, clear? held together by weak van der Waals forces. Weak van der Waals forces of attractions. Forces of what is known here? Attractions. This is the main reason. Clear? So melting and boiling point noble gases are very low, and why? Because due to these atoms of elements, these atoms are held together by very weak van der Waals forces of attraction. Clear? So when they are held very weak van der Waals attraction forces, means to break that one, we need not to supply much amount of the energy. So that's why their boiling and melting points will be low. Clear? But you know that as we are moving down the group, as size increases, clear? As the size increases, and van der Waals forces also, the magnitude of van der Waals forces also increases, and automatically melting and boiling points increases. Means the melting and boiling points increases down the group. Melting and boiling point. Clear? So melting and boiling point of noble gases increasing down the group, increases. The melting and boiling points increases down the group. We are discussing about noble gases only. So that's why the melting and boiling points increases. What is here? Down the group. You know? So means what it is, it will be. So if I take here helium, neon is less than, argon is less than, krypton, xenon is less than radon. Radon will have the, you know, high melting and boiling points. Why? Because as we are moving down the group, the magnitude of van der Waals forces increases, so that's automatically melting and boiling points increases. But here helium has lowest boiling point of all known substances. Clear? So what it is here? Helium has how much boiling point means? Helium has lowest boiling point, that is 4.2 Kelvin. Lowest boiling point of all known substances. What is my here? Substances. Clear? So this is about the melting and what is my here? Boiling points. And the next one, put the heading here, easy of liquefaction. Clear? Put the next one is easy of liquefaction. Clear? Put the next heading, easy of liquefaction. Easy of so what it is here, easy of liquefaction. Clear? So you already know that these all are gases only, and when they are gases and we have to liquefy them, what is required? And you know, strong attraction forces are required. Clear? If and there is strong or you know attraction, which attraction forces are existed among the noble gases, means one noble gas is there, and which forces existed here? And you know, weak van der Waals forces are existed. Clear? As you know, if you are moving down the group from helium to radon, the magnitude of van der Waals forces increases. If forces increases, then automatically they come together and combined and converted into liquid. Gases are converted into liquid. Clear? So that's why, and here easy of liquefaction, and it depends upon the magnitude of attraction forces. Clear? So that you write easy of liquefaction is directly proportional to magnitude of attractive forces. Magnitude of which forces? Attractive forces. You know that magnitude of attractive forces means magnitude of van der Waals forces increases down the group. So that's why, which can be easily liquefy here? Radon compared to what is helium. Because you know, radon, as the size increases, van der Waals forces increases, force of attractions increases, automatically means radon can easily liquefy, means converted into liquid. Clear? So what it is here? So R of liquefaction is equal to helium, and neon, and argon, krypton, xenon, and last one is what it is? Radon. This is. Clear? So which one easily liquefies here? And radon liquefies very easily compared to the what it is? Helium. Clear? So this is about the easy of liquefaction. Clear? So this is about what it is here? Physical properties. And the next one, we will go for chemical properties. Physical properties we have completed. How many physical properties we have completed? The first one is, you know, atomic radii, ionization enthalpy, electron gain enthalpy, and the next one is monoatomic nature, and next one is melting and boiling points, and easy of liquefaction. Clear? So put next heading here, chemical properties. These all are physical properties. Put the next one, chemical properties. Clear? Put the next heading, chemical properties. Chemical properties. Okay. So what is chemical properties? We have already discussed. Clear? So noble gases are almost chemically inert. So that's why we will call one time we have discussed in the introduction. What we have discussed, this can also be called as inert gases. because of their inertness. Clear? So that is, and you know, noble gases are chemically inert. Clear? Due to the three reasons. What are those three reasons? Are first one is because of its stable electronic configuration. Clear? And the second one is high ionization enthalpy values. And third one, and the electron gain enthalpy values are positive for noble gases. And these three are the main reasons for the chemical inertness of noble gases. Why? Because simple. If any compound 2 involved or any element 2 involved in the reaction, either it has to lose the electron or it has to gain the electron. Then only reaction takes place. Clear? And to lose means noble gases, you know, they are neither lose the electron and nor gain the electron. Why? Because to lose the electron, it has means, you know, noble gases are very, very high ionization energy. To lose the electron, you have to supply a lot of energy, and also to gain the electron, and we have to supply a lot of energy also. So that's why, and noble gases neither lose the electron nor gain the electron, so they are chemically inert. Clear? So these are the reasons. Put here, right? Noble gases are chemically inert. They are which one here? Chemically inert. Noble gases are chemically inert due to because of three reasons. What is the first reason? Because of first one is stable outermost electronic configuration. Stable outermost electronic configuration. EC means what is electron. Don't write here like EC in your book. Clear? Write electronic configuration. Clear? Second one. What is the second one here? High ionization enthalpy values. High ionization enthalpy values. High ionization enthalpy values. Clear? No? So this is another reason. So due to this high ionization energy, and due to this, you know, noble gases cannot lose their electrons easily. And the next one is electron gain enthalpy. Electron gain enthalpy values are electron enthalpy values are positive. These are the three reasons why noble gases are chemically inert. Clear? But here, until 1962, clear? So up to the means before 1962, scientists also, they have done a lot of, you know, reactions on the noble gases. They did so many experiments on the noble gases, but they are failed to get the compounds of noble gases. Clear? And in 1962, Bartlett, he has prepared, you know, the first noble gas compound. Clear? So what he has done? Clear? The scientist's name is in 1962. Clear? So in 1962, what is the scientist's name here? Neil Bartlett. He prepared first noble gas compound, but he, first of all, he has not done experiment directly with the noble gases. What he has done, he has taken one powerful oxidizing agent, that is platinum hexafluoride. Clear? And it is treated with the oxygen. Clear? So then he got here one ionic solid, that is IO2 plus and platinum F6 minus. This is one complex. The complex is what is here, solid. Clear? So what is this complex here? The complex is dioxygenide and hexafluoro platinate 5 means here oxidation number. So these are, like it is coordination compounds, like, and we have coordination compounds. There we will discuss about the nomenclature of coordination compounds also, how to write this name, and there we will discuss. Clear? So this is the reaction first he has done. As he used any noble gas? No. But what by this experiment he observed that here oxygen, it is a powerful oxidizing agent. It oxidizes the oxygen into O2 plus here. Means what it has done? It has removed one electron from the oxygen. To remove the electron, and that how much energy is required here, means that we will call it as a ionization energy. And this molecule has the energy or capacity to remove the one electron from the oxygen. Clear? So he has value, the ionization enthalpy value of oxygen is, it is around 1170 kilojoule per mole. This is the ionization energy of the oxygen. So data is available. So to remove the one oxygen from the one electron from the oxygen, you have to supply this much of heat energy. Clear? So now what he has done? So in this reaction, oxygen is losing one electron. Clear? And that oxygen having what is the ionization enthalpy value is 1170 kilojoule per mole. To remove the one electron, this much energy is required. In this, platinum is removing that electron. So now what he has done, he compared the ionization enthalpy's values with the, what it is here, noble gases. Clear? So these oxygen ionization enthalpy values are compared with the what it is here, noble gases, and now he has identified xenon is having almost equal ionization enthalpy values with the oxygen. Clear? So it is how much? 1170, 1175. Both are having same ionization enthalpy. So it is involving reaction. So he thought that this may also give this type of reaction. So by the thought, he has done experiment here. What is that one? So he has taken platinum hexafluoride and treated this one with the xenon. Clear? So then, so what he got immediately, he got here xenon platinum hexafluoride, and here this is. So what is color one here? Red colored solid he got. Red colored what it is here? Solid. He got this now. This is the xenon hexafluoroplatinum. Clear? Or you can write here xenon hexafluoroplatinate 5. Clear? So this is the first, what it is here, noble gas compound prepared in the 1962 by the Nile Bartlett. Clear? So what is the name of here? Xenon hexafluoroplatinum. Hexafluoro what is here? Platinum. Or you can write xenon hexafluoroplatinate 5. Okay. This is about the what this is means. This is the first compound of the noble gases prepared by which one? Niels Bohr. After this discovery, and their number of compounds of xenon and krypton have been prepared.